Okay, thank you, everybody. Is this good? Can you hear me? Okay, so today I'm going to talk about I/O. So this talk starts with like an inciting incident. So in 2013 or 2023, I took a trip to Marseille and I got really bad food poisoning. I was very sick and I had these kind of like hallucinations that ordinarily you need to pay like a lot of money to get. So it was either this or it was this. But I don't know which one was the culprit. But like, so people think that like your stomach is actually like a part of your brain, that like the bacteria in your stomach, it digests food in a certain way and it communicates with your brain, which like affects the way that you actually think. And after I had the food poisoning, it kind of changed my life a lot. Here are some of the changes that happened. So I started living alone. I moved to a new city to live with friends. I stopped being a digital nomad and I had a home for the first time in like 5 or 6 years. I started to focus on health. I found like peace in my life that I didn't know was possible to have. I also quit my job. And all of this was like precipitated by me having food poisoning. But I think that it was more like another contributing factor is that like I just always want more from life. Like the things that I have or the things that we have is like never satisfying for me, you know. So I'm always like searching for more. So now I'm going to talk about like some of the things that we currently have that I think are not enough. One of them is the whole programmable cryptography tool of like proof of validity. Like this is a useful tool, but like we've been using it for years, and it seems that like we're getting close to the limits of applications. Like I'm very excited that we have ZK EVMs and we have ZK rollups, and that we have this like whole proof of validity ecosystem that's growing. But I don't think that this has transformed the world in the way that I was hoping that programmable cryptography would change the world. Another thing that I'm concerned about is like ZK ID. So I spent a lot of time thinking about like, well, why was the first blockchain thing a currency rather than a reputation system? Because I thought that like, well, a reputation system is going to be much more like free and open. But the reason I think is that like reputation systems are inherently about like excluding people, and it seems that like this is a difficult thing to like build as like it seems as less empowering than a currency system, which is like free for anyone to use basically. So like I'm less excited about doing like private identity stuff, and because it's inherently about like excluding people. So like last year I spent a lot of time thinking about like what else could we have, you know, like what was the future, what was a better future for us. So this time last year I gave a talk about, it's called 2PC is for lovers, and it talks about how we can use FHE and MPC to have this like multiple party hallucinated server. We have this like encrypted computer that like you do all of the operations inside the computer and nobody knows what's going on inside. And like the talk is interesting and it digs into this idea and proposes some sample applications. But one of the big problems with this whole direction of work is that it required interaction. So like with MPC, you needed to be online in order to execute the server. And I'm currently most excited about like having servers with many people computing together. And if you wanted to have a server with like 1 million people, you just can't do that, right? Because 1 million people would have to be online at the same time and computing together at the same time, which seems to me just to be completely impractical. Because like someone is going to lose their password or someone's going to lose their phone, and you just won't be able to see the final result, or you won't be able to finish the computation. But the thing that so in order to overcome this, the tool that we need to use is I/O, which stands for indistinguishable obfuscation, which basically takes away the interactivity that we need to have for hallucinated servers up until now. So if you want to do something new, you have to do things differently. So the rest of my talk, I'm going to talk about like the different things that we're doing. So why don't we have it already? So it's hard. Like indistinguishable obfuscation has been an open problem for a long time. Recently, in 2022, the first scheme from standard assumptions was proposed, and this was a big deal in the I/O world because it was the first time that it was like even theoretically possible to do this. But unfortunately, the scheme is not practical. It would take millions of years to like execute to do a full execution of an IO circuit. But this is from standard assumptions. So in cryptography, we always try to base what we're doing upon standard assumptions. But like, actually in the cryptocurrency world, we don't really do this so much. In the cryptocurrency world, we use a bunch of non-standard assumptions that like the regular cryptography community would be very concerned about. And like 2 examples are like the snark-friendly hash functions. They use this very like crazy kind of assumption that like like the rest of cryptography doesn't really think about. And also grinding is right is another non-standard assumption. So like, well, the question is like another question to ask is like, why do we even need to assume anything in the first place? And the reason for this is that like when like P equals NP question mark is like this big open problem in computer science. It's like this kind of like millennium prize if you're able to prove like P is not equal to NP. It basically says that like some things are easy and some things are hard. And like all of the easy things, all of the hard things are not actually just secretly easy things. So because we can't prove that something is hard or something is easy, we're not able to prove that like, because we're not able to prove that anything is hard or anything is easy, we're not able to prove that like specific things are hard or easy. And because of that, we're not able to say that like, well, this problem is hard. It's hard to solve this. It's hard to decrypt this unless you have the private key. So what are current assumptions we currently use? Well, we currently use a bunch of assumptions that are based upon prime numbers. So elliptic curves is like a prime number-based assumption. And this assumption has been chosen because it's been like an open problem for hundreds of years. For hundreds of years, number theory has been trying to figure out to understand more about prime numbers and about like their distribution or whatever. And this is the assumption that like most of our cryptography is based upon because it's just really hard. Like it's been open for a long time. But like the problem is that there's a lot of complexity here. There's a lot of complexity. I want to go back. Yeah, there's a lot of complexity here in prime number because it's just like this kind of security by obscurity thing. It's this problem we've been trying to solve for years and years and years, and like no one has made any progress on it. So therefore, we think it's hard. But like I'm not like there's been like recently more people have been trying to come up with like simpler assumptions that are also like we think hard. And like lattices is an example of this. Okay, now I want to go to the next slide. Okay. So like the lattice assumption is much simpler than the prime number-based assumptions, and they seem like much more intuitively. It seems to me like much harder, but it's not like. But we can't prove it. Like we can't prove that anything is hard. So we just have to base everything on these assumptions. It seems, yeah. So like one example. So what does it take for like an assumption to become like a standard assumption? So it took about 10 years for the lattice-based assumptions to become like standard. Although like many people in the cryptography community are still very skeptical about lattices. For example, Daniel Bernstein is just like is not confident in lattice-based cryptography. Yeah, so like this slide, I don't know if I have time to go deeply into it, but it's basically claiming that like AI is more dangerous than quantum computers for cryptography, because like if AI seems to be a tool to like teach people, and that seems to me like inherently more powerful than a tool that's like able to do compute. So like I feel that like this, like I make a prediction here that like, well, in the next 20 years, AI is going to break more stuff than quantum computers will. I think this is a good bet. But like it means that like the assumptions that we previously had, we need to be more careful about, right? Because like we're going into a world where the like old this has been hard for a very long time might not remain being the case. Okay, so. Right. So like basically I've become open to using like non-standard assumptions to build I/O. And the hope is that like we will be able to, here's a list of papers, and basically the way it works is from top to bottom is from like standard assumptions to like more exotic assumptions. Yeah. And here's our implementations of the various schemes. But this is in no particular order. I should have ordered this better. Yeah. So like basically our goal is to like implement these schemes and to like break them or try to find, and then to build tools to build things on top of the schemes. So like we have a bunch. So we're announcing this bounty where we've implemented the first paper or the last paper on the list, the most like extreme assumption on the list before. It's called local mixing, and basically you can take a circuit with 1,000 gates and obfuscate it, which basically means that you add like randomness to the circuit until the circuit becomes 230,000 gates. And then basically the challenge is to take the 230,000 gate circuit and reverse it to the 1,014 gates circuit, right? So be able to remove all of the noise while maintaining the functionality of the circuit. And we claim that this is really hard. And if this is really hard, it's basically like indistinguishable obfuscation. We can build a bunch of cool stuff. So this is a bounty that we're just announcing today. And so the prize is $10,000 for someone who's able to do this. And this is a collaboration between these three groups: Random Zone, XeroXPark, and the Ethereum Foundation. Yeah, so, well, what would it mean if we were able to do I/O? We would basically finish cryptography. And the reason, like, okay, so here's how to think about this. So basically you can model I/O as like a trusted third party that you can actually trust. So you can model zero-knowledge proofs like this, but the party is more limited. So if you have a trusted third party that like does some compute and verifies the compute for you, then that's like what a zero-knowledge proof is. But with like once you get to I/O, you have a trusted third party that's able to do basically everything. They're able to verify computation. They're able to like do multi-party computation stuff. They're able to maintain secrets and only use the secret under certain conditions. So I/O is basically very close to the end of what we would need, or is close to the end of programmable cryptography. And like I don't know what I'm like. I feel like this is like the last big quest. It's kind of like, you know, that in history there was a time when people thought that there was just more land that people didn't know. Like people were like exploring the world, and there was just more places to go. You could always like go further west. But then at one point you just got like to the end of the world, and then it was like, what do you do? Like, what do those people do? Like, imagine that you're like, yeah, I want to live a life of adventure, and then you get to the west coast of the US and you're just like done. Like, what next? I don't know, but I feel like no matter what, I will not be happy, because nobody wants to finish programmable cryptography less than I do. Okay, so while you're in Thailand, there's all these opportunities to have these like life-changing experiences. So go to the night market and don't be too careful. So there's a couple more talks about this. There's 2 p.m. at stage 6 today. Jay is going to talk more about the bounty. He's going to dig into like how local mixing works and a bunch of things about like the scheme itself. Like we don't have any tools yet that people can like build applications on top of. At the moment, we're still like, we just made the simplest possible circuit, but it's reasonably practical. The thing that takes the most time is actually doing the obfuscation. To run the circuit, it's just like a 260,000 gate circuit that you execute. So like the performance is pretty good, but like that said, it is a very extreme assumption that we're building on. I think that like our plan is to sorry, let me go back and show the other papers. So we already did local mixing, but our plan is to sort of work up from like most extreme assumption and most practical, or least and most practical, to less extreme and least practical. And hopefully somewhere along the way we'll find something that like is in the sweet spot. I'm confident that we'll be able to find something that works from standard assumptions, but I think that like it's important to start. And like our goal is to like have a bounty for a bunch of these different schemes, and always have one that's not been broken, or like always have 2 that's not been broken, and just like continue this effort. Because like the lattice-based assumptions, it took like 10 years to go from being like kind of crazy assumption to more useful, or like more accepted. So we're hoping that like we'll be able to like navigate a similar trajectory here. Okay. Okay. Yeah, so there's more talks. I think on tomorrow there's a bunch of talks about I/O that would be interesting for people to check out. Yeah, I have a little bit extra time. I can take some questions, or I can talk some more if I remember some other stuff I wanted to say.
Thank you so much, Barry.
Thank you.
This presentation was very complex for my non-technical brain, but actually the audience here have added very cool questions. And the first one here that I wanted to ask was, like a definition, what's I/O, and pretty much an explanation. If you could do like an explain like M5, that would be helpful.
Sure. So I/O stands for indistinguishable obfuscation, and it basically means like encrypting a program such that you can execute the program, and you can get an output that is not encrypted. So like no one is able to see what the program is doing, but what you get out is something that you can understand. So basically, it's like FHE, but in a non-interactive way. Like another way to think about it is, I can give like the formal definition, but maybe we should go to the next question. Let's just take the next question.
Another question here. What does I/O replace ZK?
So I/O kind of includes ZK. So there's ways that you can use I/O well, it depends what you mean by ZK, because people abuse the term to mean a whole bunch of things. And like I used to do that too. Well, I don't know if I did used to do that too, but yeah. Okay, so if you mean zero knowledge proofs as just like a proof that a computation was done correctly, then it's like, yeah, you can do that with I/O, but I/O is much more than ZK. It's more powerful because, like, another way to think about this is ZK is like a single player thing that I can prove about things that I know. I can show people things that I know, and other people can show me things that they know. But there's no way to do like a collaborative proof. There's no way to do a multiplayer things, right? And like I/O basically lets you do like multiplayer stuff. So you can do like all these interesting coordination things.
Well, you got here some love from your PSE colleagues. And I have another question for you. So quantum machine learning will break more things than AI, or quantum each alone?
Sorry?
Quantum machine learning will break more things than AI, or quantum by themselves? Will break more AI or break it on its own?
I think that like AI by itself will break more than quantum computers by itself.
Does I/O not rely on any assumption?
Yeah. It does. I/O relies on a bunch of different assumptions. Like all cryptography relies on assumptions, except for one-time pad, which doesn't rely on any assumptions.
Is there any physical hard limit to how fast cryptography, ZK, etc., can get?
Yes, it can. Like ZK cannot get faster than the thing you're trying to prove. You at least have to like calculate the witness. Or you need to be able to like do the computation. ZK has that limit, and so does everything, I guess. I suppose that like you at least need to understand what you're trying to do. I need to think more about like the I/O case to have like a more coherent answer.
When will I/O happen? 1 year, 5 years? How would you define the prediction market for this?
Yeah, that sounds good. An I/O prediction market. I think that I think the key thing to ask in that question is from like what kind of assumptions. That like historically we've had a whole bunch of I/O schemes that have been from like non-standard assumptions, but they've all been broken. So I think it's just a matter of time. So that's the important thing to include if you're thinking about when you're asking this question. So from like non-standard assumptions, I think pretty soon, like it's already the case that there's practical I/O schemes from non-standard assumptions, but we don't know if they'll be broken or not. So like that's another interesting thing. We could do prediction markets of whether a particular assumption will be broken. That could be really fun. Yeah.
Do we need Ethereum if I/O works?
Yeah. I think that there's still these things kind of like add together. So there's a couple of things that IO is not able to do. One of them is like data proof of publication or data availability. Cryptography, as far as we know, is not able to make sure that you have published something, because that's like it's like an objective reality. To be confident something has been published is not possible to do with just compute. You need to have some consensus. So Ethereum is still useful for this.
What are you personally excited to work on once the end of cryptography research is reached?
I don't know. Yeah, I don't know. I feel like I'm just secretly going to try and sabotage our efforts.
Yeah, there is a lot of questions here, but I do wanted to find one, maybe like one last question. If you can compare IO with food, what would be?
I don't know.
Probably the hardest question you've got in this
Yeah,
panel.
yeah.
I see.
It seems to be some kind of like food that consumes all of the food. So like atoms. Yeah.
Okay.
Yeah.
Yeah. Okay.
Carbon. Yeah.
That's a good closing for your presentation, Barry. Thank you so much. It's very cool to learn more about IO. Everyone give it up for Barry.